In this video, we're going to take a look at the 6 logic gates, how they work, and how we can make them with transistors. But before we can make the logic gates, we need to understand how transistors actually work. Transistors have 3 legs. The one on the left, called the collector, is where the electricity comes in. The one on the right, called the emitter, is where the electricity flows out. And the one in the middle, called the base, controls how much electricity is allowed to go through. So the two ends basically form a path for electricity to go down, and the middle leg is the gatekeeper, deciding whether or not to let the electricity go through. This is an example of a transistor in action. As you can see, we have a 3-volt battery providing power and ground to these rails here at the bottom of the breadboard. The transistor is receiving 3 volts on the left side, and the right side is connected to an LED. This switch here determines whether or not electricity will be sent to the middle pin of the transistor, which in turn determines whether or not electricity will be allowed to pass through and light up the LED. So if our input, the switch, is on, the LED is on, and if our input is off, the LED is also off. Now, obviously, we could have made this circuit without the transistor, but we're going to need that transistor for our logic gates, the first of which is the NOT gate. The NOT gate is very simple. It takes an input and inverts it, so if the input is on, or true, it will output off or false. And if the input is off, it will output on. Let's make it. Here's our circuit where we can turn the LED on and off using a switch. If the switch is our input and the LED is our output, we need to invert the signal for a NOT gate. So we'll connect the LED to the collector side of the transistor instead, and we'll connect the emitter side of the transistor to ground. Now the LED is on by default because we've connected it to the 3-volt wire. However, if we activate the transistor, the electricity flows through the transistor and back into the battery through this wire instead of flowing into the LED. So the LED is now the opposite of the switch. If you'd like to check out this circuit or any of the other circuits we're going to make today, the links for all of them are in the description below. But now let's check out the OR gate. The OR gate takes 2 inputs. Let's call them A and B, but it still only gives 1 output. It will output true if one or both of the inputs are true. So if just A is on, it'll be on, or if just B is on, or if both A and B are on. The only time it'll be off is if both A and B are off. For this gate, we're going to need 2 switches and 2 transistors because we have 2 inputs. We're once again starting with a simple circuit that turns the LED on and off based on a single switch. To create our OR gate, we'll copy and paste the switch and the transistor to the upper section on the breadboard. We'll also want to extend the power wires going to the switch and the transistor to the new upper switch and upper transistor. We'll also add a wire going from the output of the switch to the middle pin on the transistor. Then we can connect the emitter of the top transistor down to the LED. Now, if either of the switches are on, or if both of the switches are on, the LED will be on. But if both of the switches are off, the LED will be off. Now we just have one more gate before things get really interesting, the AND gate. The AND gate also has 2 inputs and 1 output, but it only outputs true if both inputs are true. If just one of the inputs is true, or if neither are true, it'll output false. To make this gate, we'll once again have to duplicate the switch and the transistor, but this time instead of putting them in parallel, we'll be putting them in series. We'll connect the output of the second transistor to the LED, and we'll also power the switch with 3 volts and take the output from that switch to the center of our second transistor. Then we'll take the output of our first transistor and have it as the input for our second transistor. The last thing I'll do is connect wires from the other side of each switch to the ground rail to make sure that when the switch is on the left side, no electricity is flowing through it. And now we'll have to activate both of the switches in order for electricity to flow through. Those 3 gates are the basic gates, and the next 3 gates are harder to make and have much more interesting uses, especially the last one. Before we go through them, hit the subscribe button and the like button if you want to master electronics and programming. The NOR gate. The NOR gate is the opposite of OR, so it will output true if both of the inputs are false, and it'll output false if either input or both inputs are true. Of course, we can make it by putting a NOT gate after an OR gate, but keep in mind that there's also a way to make it from scratch that would use less transistors than combining two of the previous gates. Very similar to this is the NAND gate. This gate is the opposite of AND, so it outputs true if neither input is true, or if just one input is true, but outputs false if both inputs are true. The interesting thing about both NAND and NOR is that you can actually make all of the other gates with just NAND or just NOR. That's right, these two gates are functionally complete, meaning that we can create any logical process, or even a whole computer processor, with just one of these types of gates. This does not work for any of the other types of gates. And the last type of gate, which can also be made using NAND or NOR gates, is the XOR gate. XOR is short for exclusive OR, which is why some people write EOR, and it will output true if one of the two inputs is true and not the other. So if both inputs are false, or both inputs are true, the XOR gate will output false. You have to have one true and one false for it to output true. This strange selective process is harder to achieve than any of the other gates, but it is very useful. One way we can achieve it is by taking inputs A and B and saying A and not B, or not A and B. This is basically spelling out what the XOR gate is doing, checking if we have A true and B false, or B true and A false. XOR is used for math, error detection, and even encryption, because it turns out that being able to check if one input is true and the other is false is super useful. But that topic warrants a whole other video, which I'll put right here once I've made it. Until then, check out this video on the transistor and 5 other electronics components you might not know about.